Today we're going to learn about the rational root theorem and Descartes' rule of signs. The rational root theorem is really helpful to help us break down or factor polynomials that initially don't look factorable, or that we have not learned factoring methods for. If some polynomial has integer coefficients, then every rational solution of f of x equals 0 has the following form: p over q, where p is factors of the constant term a sub 0, and q represents the factors of the leading coefficient a sub n, including their positive and negative values. Remember how the fundamental theorem of algebra gives you the number of solutions for a polynomial equation? Well, Descartes' rule of signs gives you the possible number of each category of solutions. So positive real zeros or negative real zeros, which can help you narrow down the process when you're looking for the zeros of the polynomial. Let this be a polynomial function with real coefficients. The number of positive real zeros of f is equal to the number of changes in sign of the coefficients of f of x, or is less than this by an even number. The number of negative real zeros of f is equal to the number of changes in sign of the coefficients of f of negative x, or is less than this by an even number. For example, if your polynomial f of x changes sign 4 times, that would mean f of x has either 4 positive real zeros, 2 positive real zeros, or 0 positive real zeros. That's what this means by less than by an even number. Let's say you had 3 sign changes, then your polynomial would have either 3 positive real zeros or 1 positive real zero. Determine the possible numbers of positive real zeros, negative real zeros, and imaginary zeros for this polynomial. To do that, we will use Descartes' rule of signs. Descartes' rule of signs, so first count the sign changes in f of x. Your first term is positive, your second term is negative. That is one sign change. From negative to positive is another. From positive to negative is another. From negative to negative is no change. Negative to negative, no change. Negative to negative, no change. F of x has 3 sign changes. This means f of x has 3 positive real zeros or 1 positive real zero. Now let's look at the changes in sign of f of negative x. Plug in negative x instead of your x's, then simplify and check for sign changes. Remember, a negative to an even power is positive, but a negative to an odd power is negative and will therefore change the sign of that overall term. Now continue to simplify. Time to test the sign changes in f of negative x. We go from positive to positive, which means no change in sign. Positive to positive. Here is positive to negative, we have 1 change. Negative positive, another 1. Positive negative, another 1. F of negative x has 3 sign changes, which means f of x has 3 negative real zeros or 1 negative real zero. We can actually set up a table to figure out how many of each category of 0 there could possibly be. Because the degree of this polynomial is 6, fundamental theorem of algebra states that we will have 6 total zeros. For positive real zeros and negative real zeros, we have 3 or 1. So we could have 3 positive real zeros and 3 negative real zeros, which would mean 0 imaginary. 3 plus 3 plus 0 is 6. New combination, we could have 3 positive real zeros, 1 negative real zero, which would make 2 imaginary zeros in order to get a total of 6. Or you could have 1 positive real zero and 3 negative real zeros, which would give you 2 imaginary zeros to give you a total of 6. The last combinations of the amount of zeros from each category would be 1 positive real zero, 1 negative real zero, and 4 imaginary zeros. And that's how Descartes' rule of signs can help you categorize the types of solutions. For number 2, we're going to find the zeros of x cubed minus 8x squared plus 11x plus 20. First, I notice that I have 4 terms. I always want to try factor by grouping if I have 4 terms. But this one cannot be factored by grouping. What would Descartes' rule of signs say about this polynomial? There's 1, 2, two changes in the sign of f of x, which means f of x has 2 or 0 positive real zeros. Now simplify. Remember, an odd exponent means we change the sign of the term, and an even exponent means the sign does not change. Now we have 0, 0, and 1 sign change. Because f of negative x has one sign change, that means we have one negative real zero. Not 1 or 0, exactly 1. I'm going to use the rational root theorem. The rational root theorem states that your rational roots will be in the form p over q, factors of the constant over factors of the leading coefficient. So I need to know what is my constant and what is my leading coefficient. The constant term is the one at the end, which is 20. The leading coefficient, the coefficient of the degree term. P includes the factors of 20, including positive and negative factors. So we could have 1 times 20 or negative 1 times negative 20. So I'm going to include positive negative 1 and positive negative 20. I like to write them in order, but it doesn't matter as long as you get all of them. The other things that could multiply to give me 20 would be positive or negative 2 and positive or negative 10, or plus or minus 4 and plus or minus 5. Q would be the factors of a sub n, our leading coefficient. That would just be positive 1 times positive 1 or negative 1 times negative 1. Now we need to set up all possible combinations of P over Q. This means our possible rational zeros are any combination of numerator over denominator. So plus or minus 1 divided by plus or minus 1 is plus or minus 1. Then we have plus or minus 2 over 1, plus or minus 4 divided by plus or minus 1, and so on. Now, obviously, these aren't all zeros, but I know that any rational zeros for this polynomial will be in this list. So what I'm going to do is test out one of these zeros. To test if a number is a zero of a polynomial, we're going to plug it in to that polynomial and see if we get 0. Or we can use synthetic division to do that. Set up your synthetic division. Let's choose one of our possible rational zeros to test. I'm going to use 1. Just like dominoes, the first one has to fall. Multiply diagonally and add vertically. Because your remainder is not 0, 1 is not one of the zeros of your polynomial. Let's try negative 1. Look at that, our remainder is 0, so negative 1 is a zero of our polynomial. Now I have found one of the 3 possible zeros, and at least one of those is a rational zero of negative 1. Because x equals negative 1 is a solution, the factor that corresponds with x equals negative 1 is like doing the zero product property backwards. So make this equal to 0 now. Now if you have multiple expressions that equal 0, you can multiply them together and make that equal to 0 and still have a true equation. That is the first factor for this polynomial that I know. So I'm going to factor out x plus 1. But how would I divide this by x plus 1? You already did that. You divided this polynomial by x plus 1 when you did synthetic division where k was equal to negative 1. So if I factor out or divide x plus 1, the other factor is x squared minus 9x plus 20. At this point in time, we find the remaining 2 solutions. Since this is a quadratic, we can use any method we want to solve a quadratic equation. Factoring is usually the most efficient, so I'll try to factor this. Remember, this remaining polynomial is still equal to 0, so you can still use the zero product property to find the remaining solutions. Your other solutions are 4 and 5. Your full factorization is the product between x plus 1, x minus 5, and x minus 4 equal to 0. Make sure you not only can find the solutions, but you can also write out the full factorization. That would be factorization with linear or irreducible quadratic factors. If this quadratic wasn't factorable, I would have to try another possible rational zero. And that's when Descartes' rule of signs would really help me narrow it down. Because I know that x equals -1 is a solution, and from Descartes' rule of signs, I only have one negative real zero, then I wouldn't need to try out any more of the negative possible rational zeros. And was Descartes' rule of signs correct? Yes, we have one negative real zero and 2 or 0 positive real zeros. 2 in this case. For number 3, let's start with Descartes' rule of signs. Check the sign changes of f of x. Positive to positive is 0. Oh, it looks like there are no sign changes here. This means our polynomial has 0 positive real zeros. Let's check the sign changes for f of negative x. One sign change, one sign change, and one sign change. That means our solutions include either 3 or 1 negative real zeros. Now let's try rational root theorem. A sub 0 is your constant, a sub n is your leading coefficient, p is factors of a sub 0, and q is factors of a sub n. Remember, our possible rational zeros include all combinations of the numerator and the denominator. Plus or minus 1 divided by plus or minus 1 was plus or minus 1, but then also plus or minus 1 divided by plus or minus 3. So plus or minus 1/3 is an option. Plus or minus 3, and then plus or minus 3 divided by plus or minus 3 is plus or minus 1, so we don't need to write that again. Plus or minus 7, then plus or minus 7/3. But remember what Descartes' rule of signs said? There will be no positive real zeros. That cuts our possible rational zeros in half, which can definitely expedite our dividing process. It's time for you to test these possible rational zeros. I'm going to start with -1. If -1 does not prove to be a solution, then I'll move on to -1/3. I want you to try to keep synthetic dividing until you find which one of these is one of your actual solutions. Yay, we found our solution is -3, which means our factor is x plus 3, based on the factor theorem. And what do you get when you divide this polynomial by x plus 3? You get 3, 4, 7. So let's go ahead and write that as a polynomial. 3x squared plus 4x plus 7. Finding that first rational zero unlocked our new quadratic factor of 3x squared plus 4x plus 7. To finish solving this problem, we need to solve this quadratic. Try factoring or use whatever method you prefer for solving quadratic equations. Because this is not actually factorable, I'm going to use the quadratic formula. So our other solutions are -2 plus I root 17 over 3 and -2 minus I root 17 over 3. Because we could not factor this quadratic equation, this is the full factorization of f of x. And remember how Descartes' rule of signs told us we either had 3 negative real zeros or 1? And it turned out that one of our solutions was a negative real zero and 2 imaginary zeros, giving us our total of 3 roots, zeros, or solutions.